So this second video, just a couple more examples of things that I've seen on the AP exam that deal with vectors or motion. This first one, example 3, gives us a position sort of like parametrically, right? I mean, it gives it x in terms of t and y in terms of t, and actually it says parametrically, so they're perfect. So when we're trying to find the slope of the path, which is like the derivative, right? We need to look at both the change in y and the change in x, but then we're going to write it as a velocity vector as opposed to like a derivative expression like we do parametrically. So I still need to worry about the derivatives. So I could still find out what is dy dt. So dy dt is chain rule 2 cosine of 2t. And then I would need to know what dx dt is. And so dx dt is equal to 1, or so it'd be like 2 over 2, so 1 t. So then if I want to look at the slope of the path at pi over 6, so then that would be, so if it's just a slope of the path, I could do dy dt divided by dx dt. The vector part will come next. And so then when I put in pi over 6 into that expression, that's 2 times cosine of 2 pi over 6's, which is pi thirds, over pi over 6. Now, pi thirds is a 60-degree reference angle. So then the cosine of that would be 1/2. So we get 2 times 1/2, which is 1 over pi over 6, which we could say that it has a slope of 6 to pi. So that part, is just looking for the slope of the path. But now as a velocity vector, we want to write that as a vector valued function. So for part B, I just take those two components of velocity, but I still, even though I think of them as like rise over run as component form, I still need to think about them as x comma y. So the x component would have been t. That's the change in t over time. And then the y component would be 2 cosine of 2t. So that would be the vector that represents the overall velocity. And then if we want to know the vector at pi over 3, so at pi over 6 this time, still pi over 6, sorry. At pi over 6, we would say, well, at, pi over 6, and then when you plug that value in, we get 1. So it's just breaking down those two components. Okay. So part C says, what is the speed of the particle at this time? So for speed, remember, we want to think about it as the absolute value of that particular velocity. And so then we think about that in terms of the magnitude of that vector. So when I do the magnitude of the vector, so to find the magnitude of this vector, it's really just the Pythagorean theorem, right? So it's the magnitude of that. So it's the square root of pi over 6 squared plus 1 squared. And so that would give us the speed of that particular vector. Now, if you do that pi over 6 squared plus 1 squared, and then, and take the square root, you would get that value. So let me do that together with you. Square root of, let's see, pi squared, find my pi key, there it is. So pi squared divided by 36 plus 1, and then under the square root. So I'm getting a speed of 1.129 if I round that. Okay. And then part D says set up an integral expression to represent the distance traveled. So now I want to think about total distance. It's not asking for displacement. So a vector to represent that part would be the integral from 0 to 5, and then we take a look at our the velocity components, and we just sort of we're going to accumulate all of those values. So our x component, if I think about that as a side of the triangle, so it'd be t squared, and then I would add that to this, 2 cosine of 2t squared dt. So again, you're looking at your velocity vector and you're treating it as I guess like a right triangle. Like the x component goes over t and the y component goes up to a value of 2 cosine of 2t. So if you're wanting to know what is that total distance then we're looking for the hypotenuse of that value. And so total distance should be absolute value, but again, because it's square rooting a sum of squares, it's still already going to be positive. Okay, and you could type that in your calculator, get a value, that's fine. Okay, so then example 4, what I'm looking at next is sometimes they give you a vector valued function that you integrate. And it looks sort of awkward, but all that's asking you to do is take the integral of each of the components. So we would have to integrate the this value here, and then we'd have to integrate that value there. So when I do that, if you look at the x value, this is a great review for the AP exam because that's a partial fraction. That's if I factor the bottom, that's t minus 5, t plus 4. So if I integrate that value, I'd want to find the partial fractions first. If we could just go through that. So that 9 over t minus 5 times t plus 4, like that should equal a over t minus 5 plus b over t plus 4. And so that means that 9 equals a times t plus 4 plus b times t minus 5. And when you choose appropriate t's, like choosing t equals 5, we get 9 equals 9a. So that means we do get a equals to 1. And then we choose t equals negative 4. We get 9 is equal to negative 9b. So it means b is equal to negative 1. So that worked out really nice. So when I integrate those partial fractions, so 1 over t minus 5 plus negative 1 over t plus 4, I'll get the natural log of absolute value of t minus 5 minus the natural log of absolute value of t plus 4, and then plus, you'll have some coefficient plus c. And so then you could combine those logs if you wanted to. So t minus 5 over t plus, t plus 4. There it is. And t plus 4 here. Plus c. So then I would use that to represent the x component of my vector. And then to get the y component, we need to integrate cosine squared of 6t. So this one's a good review of half angle. All right, so the integral would be, I could write that as 1/2. It's cosine, so it'll be plus 1/2 cosine of 12t dt. And then, so then I integrate that. That's 1/2 t, plus 1/2, and there's a 1/12 by the chain rule sine of 12t plus a constant. So we're getting that 1/24. So then the component vector form of this would be the natural log of t minus 5 over t plus 4 plus some constant. And then it would be 1/2 t plus 1/24 sine of 12t plus another constant. And I might call this like constant 1 and call this constant 2 because they don't have to be the same constant. Okay. So again, you might see integrating a vector, you just integrate the components, which is pretty straightforward. Okay. Now example 5, it gives us an acceleration vector, and it basically wants us to find some position and velocity values. Well, that is a direct application of what we just did, where if we want to go from our acceleration vector to our velocity vector, we're going to have to integrate. And the fact that they give us some specific values for velocity, that's going to tell us what those constants are going to be. Remember how we had 2 separate constants in the last example. So if I integrate acceleration as a vector, That means I need to integrate each of the components. So I'm integrating the vector 6t and the negative sign of 2t. Now, luckily, this is a lot easier of an integral than our previous one. So that becomes the vector 3t squared plus some constant. And then this would be, it would be a negative, so positive cosine of 2t, but there's a chain rule, so it'd be like 1/2 cosine of 2t plus another constant. So call that constant 2, constant 1. Now, the given of this velocity at 0 is 2, 1. That's going to allow us to solve. So if I put in 0 for t, so that means that 3 times 0 plus our constant is going to equal 2. So in that constant 1, that value is going to be 2. And then when I put in 0 to the second value, right? So 1/2 cosine of 0, which is 1, plus our constant 2 is going to equal 1. So now I know our constant 2 equals 1/2. So if we need to find the values of v3, I now know at least, okay, well, at least my velocity vector is equal to 3t squared plus 2, and then 1/2 cosine of 2t plus 1/2. So now when I'm evaluating v of 3, I can just put in 3 into that component. So 3 squared is 9. 9 times 3 is 27. And then 27 plus 2 would be 29. And then, without a calculator, I would just have to leave it as like cosine of 6, right? So I could say that's 1/2 cosine of 6, and then plus 1/2. Okay. Then we also need to know position at 3. So we need to integrate our velocity derivative. And notice they do give us one more set of data points. So that's going to allow us to solve for those constants. So now I'm going to integrate, right? So much in this one problem. So now I'm going to integrate our velocity. So I'm going to integrate 3t squared plus 2, comma, 1/2 cosine of 2t plus 1/2. So, and with respect to t, don't forget that. So when I integrate that, now that becomes t cubed plus 2t plus some constant there. And then this one becomes, another extra half here. So it becomes 1/4, like 1/2, 1/2. So 1/4 sine of 2t plus 1/2 t, 1/2 t plus a constant there. And so let's substitute our values in, right? So we substitute at 0, we get -4, 0. So at 0, so 0 plus 0 plus our constant, we should get -4, which tells us that that constant is -4. And then when I plug in 0 here, sine of 0 is 0, plus 0, plus our constant 2, it tells us that is equal to 0. So we know that constant 2 is 0. So now I can actually have my position vector as a vector valued function of t cubed plus 2t minus 4, and then comma 1/4 sine of 2t plus 1/2 t. And now I can evaluate s of 3. And so s of 3, the vector evaluated at 3, is equal to, let's see, 3 cubed is 27. 27 plus 6 would be 33. Minus 4 is also 29. It's ironic. And then, again, we don't really know what sine of 6 is, so we just leave it as 1/4 sine of 6 plus 3/2, that vector right there. And if we wanted this, like I'm thinking back to the velocity vector, if we wanted that as a speed, we would take the absolute value of that. And I probably should preface that, just as a summary here for that problem, that speed, because it does come up, Speed would be the magnitude of that vector, and you find the magnitude of a velocity vector by doing like the x component squared, so the x of t component squared plus the y of t component squared. So speed is the magnitude of a velocity vector. Okay. So then I think the very last one, I think just to see in case you do have it with i's and j's, it's the same concept that suppose the derivative equaled this coefficient of I, which represents in the x direction, and this coefficient of j, which represents the y direction. If you want to find like going from the derivative back to the function, we need to integrate that. And this is sort of like giving us that initial like, oh, at 0, these are our respective coefficients. So if I integrate the derivative of r as a vector with respect to t, that just means I have to integrate each of those components. And so, this component right here, that's arcsine, so that's not too bad. So then r as a function would be arcsine of t plus some constant. So that represents the I component. And actually, I should put that. So arcsine of t and that's an I component, like that. And then to get the other value, if I integrate the square root of 4t plus 1, I might want to use just a u substitution there. So let's let u equal 4t plus 1. The derivative is 4 dt. So 1/4 du is equal to dt. So then when I integrate that, it's really like 1/4 the square root of u dt or du. So then that's 1/4 u to the 3/2 over 3/2, which is taking it times 2/3. But then we had that as a root, which is great. Okay, so then that would be 2/12 or 1/6. So I get 1/6. And then that's 4t plus 1. Sorry, I started writing t. I meant to say 4t to the 3/2 power plus c, component 2. And so then that's your j, so to speak, your j component. So then when we look at 0, we know that we're going to get a 3 for this first component. So when I put in 0 for t, so I know that arcsine of 0 is 0, and plus some constant is going to equal 3. So then we say, so 0 plus some constant of our I is equal to 3. So that means that my constant must be 3. So that's nice. And then the other one was -1. So then when I put 0 into this value, so I get 1/6, and that's 0 plus 1 is 1. 1 to the 3/2 is still 1. So plus some constant 2 for your j component is equal to -1 for your j. I can put the I there. So you can kind of solve for that. So that means I know that 1/6 plus c2 is equal to -1. 1/6 plus c2 is equal to -1, which means c2 is -7/6. Okay, so our final answer then, putting that all together, would be our r as just a function is equal to the quantity arcsine of t plus 3 will always be your I component, plus, and then we said 1/6, and then it's 4t plus 1 to the 3/2 power minus 7/6 as your j component. And again, make sure that, I'm going to highlight this here, make sure that all of that is within, for what you're going to call the I coefficient, and all of that is what would be in your j coefficient. And again, if I was going to ask something about find speed, I had a vector velocity like that was given, I do the absolute value of the components squared. What we just found is more of that is finding the position vector.